Hello everyone. So now we'll start solving the chemistry solutions. Okay, let's get started. Okay, the first question. Okay, let me take a pen. It's pen and oh, it's not. Okay. Which of the following compound is ionic in nature and soluble in water? Okay. So if you are someone who is seeing this video, like CUET, your Common University Entrance Test question paper actually has 100 questions. Okay. And first 25 question comprises of your general aptitude. சரியா so first 25 questions வந்து we solved in detail in a different video. So you just go and see that video if you want to solve general aptitude, or else you can go to start with this video itself. Okay, yeah. First question, that is 26th question. Which of the following compound is ionic in nature and soluble in water? Okay. So what are the options they have given? They have given 1 bromo, cyclohepta, 2, 4, 6 triene. So let's draw the structure. So we have a cycloheptatriene, which is a 7-membered ring. So we have our 7-membered ring like this. So 1, 2, 3, 4, 5, 6, 7. Okay. And what they have given? They have given 1 bromo. So 1 we have bromo, 2, 4, and 6. 2, 4, and 6 we have a triene group. Okay, which is nothing but a 3 double bond groups. Okay, this is the structure. This is the structure for 1 bromo cyclohepto heptatriene. Okay, second structure, which is 3 bromo heptatriene, only heptatriene. So 1, 2, 3, 4, 5, 6, 7. Okay, so 2 comma 4 comma 6, 3 bromo. Okay, this is the second structure, and third structure is pentadiene. uh, so 1, 2, 3, 4. 1 comma 4, 3 bromo pentadiene. Okay, and then we have cycloheptadiene, cyclopenta, 1 bromo, 2 and 4. Okay, so these are the structures for the given options. Okay, now let's get back to the question. என்ன கேட்டிருக்காங்க? They are asking about the ionic nature and water solubility. Okay, so basically whatever compounds we have, we need to create ions out of it. எடுக்கிற compound வந்து என்ன பண்ணும்? We have to create ions out of it. We all know bromine is a very good living group. Okay, so what happens? This will remove, and this is going to form a negative charge here, and this is going to form a positive charge. Likely, if you break, everything is going to form ions. So we have no doubt everything is ionic in nature. All these compounds are ionic in nature. But then here comes the very important question: soluble in water. Okay, soluble in water. So how we can say a compound is soluble in water அப்படின்னு பார்த்தீங்கன்னா, it depends on your SN1, which is solvolysis. Okay, so என்னன்னா, if your carbocation is stable, if your carbocation is stable, then that is what is soluble. Okay, if your carbocation is stable, then that is water soluble. So we need to find which carbocation is more stable in nature now. Okay. So let's start with the first option. In the first one, what we have? We have a cyclo heptatriene group. Okay, with one positive charge. So we know that how many double bonds are there? There are 3 double bonds, which means 6 pi electrons are there. So this follows 4n plus 2 rule. This follows 4n plus 2 rule. So this is aromatic in nature. And we know that aromatic compounds are highly stable. Okay, aromatic carbocation is highly stable. So this is going to be water soluble. So your option 1 is the correct answer. So if you look at the second and third option, these are not even aromatic structures. These are stabilized by your hyperconjugations. And we know that aromaticity always comes first, then comes your hyperconjugation, inductive effects, and everything comes next. Okay, if you look at the fourth option, which is 1 bromocyclopentadiene, yeah, Here, if you see here, you have a positive charge. Okay, so which means on total you are going to have 4 pi electrons. That means this follows 4n rule only, which is anti-aromatic. Which is anti-aromatic. So this carbocation is not going to be stable. So 4 cannot be the answer. Okay, it's only about your SN1, solvolysis, and aromaticity concept. As simple as that. This is a very simple question. Next question. Generate molecular orbitals in molecules consisting of three or more atoms. Which of the following is correct? Okay. So first option என்ன கொடுத்திருக்காங்க, they have given group orbitals are first generated by combining atomic orbitals with same symmetry. Okay. Second option பாருங்க, second option is contradictory. So here they have seen the group orbitals are are generated by combining different symmetry. Okay. And then so what we can say from this is that question வந்து என்ன சொல்லியிருக்காங்கன்னா, they are asking which is the correct answer. Either this can be correct or this can be correct. So this is a 50-50 one. Okay. So this is going to be a 50-50, and group orbitals can be treated as molecular orbitals of the molecule. See here we are talking about three or more atoms. So in this case your group orbitals cannot be treated as molecular orbitals of the molecule. So 3 is wrong. And then your linear combination of atomic orbital method is actually applied. Okay. So fourth is also wrong. So let's come to the first two options. So we know that according to Hull's rule, even if we want to form any orbitals, if you want to form any atomic orbitals or anything in general, first the atomic orbitals of same symmetry or your electrons of same symmetry should be filled. Okay, then only you can change the symmetry of the orbitals. Okay, so from this we can say option 1 is the correct answer. Next question. A 60-watt electric heater was immersed in a gas tank, taken in a constant volume adiabatic container. Okay, and it was switched on for 150 seconds. The temperature of the gas increased by 5 degrees Celsius, the heat capacity of the gas. Okay, so now what they have did is they have taken a adiabatic container which maintains a constant volume. Okay, in that they are putting a 60-watt electric heater into that container. So electric heater and the container குள்ள போட்டுட்டு and they are switching it on for 150 seconds. So 150 seconds the temperature is increased to 5 degrees Celsius. Now they are asking the heat capacity of the gas. So what is the heat capacity experienced by the gas inside the container? That was the question. So basic formula we know that dq, change in heat, is equal to heat capacity CD, because we are talking about constant volume. Okay, constant volume heat capacity and change in temperature plus PTP. So we know that they have given adiabatic container with constant volume. When they say constant volume, your dV term is going to be 0. So this entire term is equal to 0. So this is a very common question, and now equation. From this we are deriving. Okay. So from this we are deriving the heat capacity. Your CV is equal to change in heat by change in temperature. Okay. This is the formula for your heat capacity. Now we just need to substitute the values. So what we know, they have given power. So they have given power as 60 watt. 60 watt. And we know that power is nothing but energy by time. So power is nothing but your energy by time. Energy by time. So your 60 watt is actually your power, and we don't know about the energy, but they have given time. So they have given time as 150 seconds. Okay. So in order to find energy, you need to simply multiply 60 watt into 150 seconds. Okay. And 1 watt second is nothing but your 1 joule. So if you multiply, you will get the energy around 9,000 watt seconds. Okay, so which is also called as 9,000 joules. So your energy is going to be 9,000 joule, which is nothing but your change in heat, dq. So this is your change in heat, dq. And what they have said, there is a increase in temperature by 5 degrees Celsius. So they have told the word, they have mentioned the word increased. They haven't given a direct temperature. So if they have given a direct temperature, then you have to plus with you have to add 273. They have only said about increase. இங்க வந்து increase மட்டும் தான் சொல்லியிருக்காங்க. ஸோ அப்போ என்ன ஆகும், your change in temperature is actually going to be 5 degrees Celsius, which is going to be 5 only. So your heat capacity is equal to 9,000 joules, okay, divided by your change in temperature, which is 5, which is going to be 5 Kelvin, okay. So why I say in Kelvin is just because, let's say, assume I'll take our ideal temperature as 298, okay, or 25 degrees Celsius. So your 25 degrees Celsius as a normal temperature, and that temperature is actually increased to 30 degrees Celsius. So that's what they have said, right? Initially, the temperature was increased by 5 degrees Celsius. So initially, your temperature is going to be 25 degrees Celsius, and it is going to increase to 300 degrees Celsius. Now let's try to convert this Celsius to Kelvin. If you convert this, what is going to happen? This is going to be 298 Kelvin, right? And this is going to be 2, sorry, 303 Kelvin. This is going to be 303 Kelvin. So now if you subtract, you are going to get the change in temperature as 5 Kelvin. So your change in temperature is going to be 5 Kelvin. So that's why I put Kelvin here. I don't mention degree Celsius. Okay. This is really important. So if you solve, you are going to get the value around 1.8 into 10 power 3. Okay. 10 power 3 joule Kelvin inverse, which is nothing but your 1.8 kilojoule Kelvin inverse. So option 1 is the correct answer. Okay. Next question. In non-polar aprotic solvent, which of the following will act as a strong base? So they are asking about the strong base. So first let's try to understand two different terms. There are two different terms in this question. One is non-polar, the other one is aprotic. So what is non-polar? What is aprotic? So polar solvents are something which can be easily dissolved in water, or which can actually form ions easily. Okay. So if you can remove, like if you can differentiate, if you can form ions out of this solution, then that is going to be, if there is any polarity, your polarity or your dipole moment also describes your uh, polar nature of the solution. Okay, so polarity is nothing but creating ions out of the solution. So if there is a high dipole moment, this is going to have the polarity. So if you see option 1, 2, 3, 4, in all these options, there is no possibility for creating a polarity, just because it is really hard. So they haven't given any good leaving group. So there is no good leaving group in this four compounds. So all these four compounds are non-polar in nature. Okay. So now we have to find what is aprotic. So, what is protic then? So, protic are compounds which has NH and OH bonds, which has NH and OH bonds, which means that your NH bond can be broken easily. So, if we can break, so அதாவது if we can break NH bond வந்து break பண்ண முடிஞ்சா, and still if that compound is going to be stable, then we call it as protic. Okay, if we cannot break NH bond or OH bond, and if by breaking it, if the compound is going to be unstable, so we call it aprotic. Okay, simply by breaking NH bond, whether we are just going to see whether the compound is going to be stable or not. If it is stable, it's going to be protic. If it is not stable, it is going to be aprotic. Okay, and they also have clearly given about strong bases only. They have given many nitrogen based compounds. Okay, so how a base will act? A base is something which abstract proton. Base is something which abstract proton. Okay, so that means it should be electron rich. Your base is electron rich. Okay, so let's see. If you see the option one, this nitrogen has two hydrogens. Okay, so there is a possibility that one of the hydrogen can leave and it can form a charge on top of this nitrogen. Okay, so there is a breaking of NH bond possible. So this is not aprotic. Likely your compound. Again, look at the second compound. This is a pyrrole. Yeah, this is a pyrrole. So if you see, we have NH bond. Okay, so if you break NH bond, this is going to form a negative charge on nitrogen, and this if there is a like negative charge in a 5 member ring, so on to altogether this is going to have a 6 pi electrons now. So this is going to be aromatic. So again this is going to be stable, so this is going to be your aprotic. Sorry, this is going to be your protic. So this is protic, this is also protic. Okay, so if you see your third compound, there is no possibility, if you, even if you break this bond, NH bond, there is no substitute to stabilize this one. Okay, in case of your one, this double bonds can rotate and can stabilize. Likely here also, your double bonds can stabilize the compound. But in case of option 3, there is no extra stabilization. So this is going to be unstable if you break NH bond. Okay, va? NH bond break panna என்ன ஆகும்? இந்த compound வந்து stable இருக்காது. So option 3 is the correct answer. If you see option 4 we don't even have NH bond or OH bond. So this is also going to be aprotic. Okay, sorry, this is also not going to be a protic. This is actually going to be a protic, which means that here your CH bond can be broken and it can form charges. It will have a carbanion and which will be again stabilized. Okay, so this is going to be your protic. Next question. Given below are two statements. Okay, one is labeled as assertion and the other is labeled as reason. So assertion என்ன கொடுத்திருக்காங்கன்னா, for a binary solution the chemical potential of one component of the mixture cannot change independently of the chemical potential of the second component. So what is this? This is your Gibbs-Duhem equation. Okay, and the correct equation is given here. So this is your Gibbs-Duhem equation. Okay, so Gibbs-Duhem equation states that the chemical potential of one component of the mixture cannot be changed. That means if you want to change the chemical potential of Na, it cannot be changed independently, but by changing this, you'll also have a equal impact on Nd. This is the actual explanation. Okay, so with this we can say option 1 is the correct answer. Both A and R are correct, and R is the correct explanation for A. Next question. 31st. Von Arkel Bohr process. Okay. For purification of metal is based on thermal instability. So see, these are something which majorly comes from your metal purification. That is your P block. Sorry, metal preparations. Okay, D block, F block, and everything. Okay. So, one alkyl Bohr process is typically for your typically used for the purification of titanium and zirconium. Okay, what they do is like they'll heat the titanium and zirconium, impure metals of titanium and zirconium with iodine, so that like they'll get the purified titanium and zirconium. So in this process there will be a thermal instability of iodides, which actually makes the metal purified. Next question. Huh. Find out the total number of stereoisomers in the following molecule. Okay, so they have given a molecule. Now you have to find the total number of stereoisomers. The best way to find out is to find number of chiral carbons. So first we need to find number of chiral carbons. So what is chiral carbon? Chiral carbon is nothing but uh, okay. Chiral carbon is nothing but a carbon attached with four different groups. So if you see here, this carbon, okay, this carbon is attached to four different groups, okay, one, two, and there is a third group, hydrogen. Sorry, fourth group, hydrogen also, okay. So this carbon attached to four different groups, so this is going to be chiral. Again, if you see this carbon, this is again going to be chiral. This will have hydrogen like this. This is going to be chiral. And the next chiral position is here. You can see. So here it already attached with one, two groups. Okay. Three groups, and then there is going to be one more hydrogen. So this molecule has three chiral centers. So what is the formula for total number of stereoisomers? 2 power n, which is nothing but n is equal to number of chiral carbon. So we can say 2 cube, which is nothing but 8. So the total number of stereoisomer is 8. Okay. 33. What is the relation between the following pair of compound? Okay. So they have given a compound, what is actually seen. So you can see that here NH2 and acid was in plane, and then the second compound, these two are in these two are not in plane. So what could have been happen? Okay, either we can rotate the bond. So if I say I'm going to rotate this bond, what is possibly, or what we can do possibly? Okay, so we can rotate the bond by C3 axis. C3 means with this, okay, or you can use a C3 axis on any other direction also. Either you can keep NH3 as the axis, or you can keep acid as the axis, okay, or you can keep any other thing as an axis, which means that if I keep NH2 and as an axis, this will not be uh, these three will be changed, your NH2 will not be changed, okay. So yeah, but yeah, but the best way, I think we can go with the options. What they have given? They have given enantiomers, homomers, identical, and diastereomers. So first, let's see whether this compound is enantiomers or not. How we can say a compound is enantiomer when the compound has a then the compound is non-superposable mirror images. Okay, so let's try to get the mirror images. Okay, so we have a compound NH2 COOH, okay, and this is going to be hydrogen, and this is going to be your CH3. So if I draw the mirror image is going to be plane. Plane groups are not going to change, will remain in plane, okay, and the other groups will be changed. So you'll get the hydrogen here, and you'll get the CH3 group below, okay. Now what we have to do, now we have to compare 1 with 2. Still the groups are in a different plane. Now we are going to simply rotate the planes, okay. So what I'm going to do is I'm going to rotate it in the anti-clockwise, or you can rotate it in the clockwise. So if you rotate it in the clockwise, it's going to be again in plane, so I'm going to rotate it in the anti-clockwise. So which means that now your NH2, so your NH2 will be in the top face, and your this, okay, again this is a plane, so this will be in your bottom, this is going to be in your planes, CH3 and H, okay. So the actual representation will be like this. So you'll have your hydrogen, you'll have your CH3, you'll have your NH2, will have your COOH. Now, just by rotating the bond, what is happening is like this is going to occupy, NH2 is going to occupy the above position, hydrogen is occupying the in plane position, COH acid will be occupying your below position, and CH3 will be occupying your plane position. That's what written. So with this, we can say that the option 3 and option 2 are non-superimposable mirror images. So we can say straight away this is going to be an enantiomers. When we can say a compound as homomers, we can say compound as homomers only when if it has a sp3 hybridized carbon. Okay, if it has an sp3 hybridized carbon, then we can say that is going to be a homomer. And identical, for in order to be identical these has to be in a different plane. So now these are enantiomers, but rather if they two are very similar, then that is going to be identical. Diastereomers needs two or more stereocenters, at least one or more stereocenters. Okay. Yeah. 34th question. For a particle in a square box of side L and quantum number n1 equal to 1, n2 equal to 2, the most probable location of the finding the particle. Okay, this is a very good question just because this is not about your 1D box, it's about your 2D box. Okay, so what is 2D box? Your 2D box is going to be like this, which means that this is going to be your x-axis and this is going to be your y-axis, and they are also telling you to finding the particle where you can exactly find the particle. So let me draw the structure. They have given n1 equal to 1. So if I say this is n1, okay, I'll draw it even bigger and correct. Okay, this is going to be your x-axis, this is going to be your y-axis. They have said n1 equal to 1, which means that we are going to have n1 value equal to 1. So which means either it can be x-axis or y-axis. So if I say I'll take it as x-axis, this is going to be like this. This is your n1 equal to 1. Okay, so this is going to be value 1, 0 to 1. So this is going to be n2 equal to 2. So n2 can be here 1 and 2. So we have if you want to find a probability, so you typically in 1D box you can say that n1 equal to 1. When we say n2 equal to 2, this is going to be the plot. Okay, but if we want to find the probability plots for this n2 equal to 2 will be like this. This is your probability for finding n2 equal to 2. So which means that this is going to exactly interact here, and then it's going to actually interact here. So the 2D box is actually drawn like this. This is your 2D box. Now we have to find where the particle is present. Okay. So what happens is the most highly we can find where is it's at the center. For like just separate this one into a two different thing. Consider it as first as a 1D box where your 0 and 1 is the length. With that you can say exactly at the middle you can find it the maximum. So I didn't draw it perfectly, it should be like this. Okay, so exactly at the middle you can find the maximum. So if I say the length is 0 to L, so this is going to be L by 2. Okay, likely if I say for 2D box, sorry, 0 to 2 as a 1D box. Okay, now I'm telling 0 to 2 as a 1D box, consider. Okay, 1D box of again length 0 to L. Okay, so நான் வந்து I change the value of 2 as L னு change பண்ணிருக்கேன். So in that case where we can find the particle, so this is going to be exactly L by 2. So this is going to be even half of L by 2, which is L by 4. So the probability of finding the particle is exactly here. This is the place you can actually find the particle in a 2D box. In a 2D box, you can find it in the length between L by 2 and L by 4. So we can say that option 1 is the correct answer. So likely if they have given for 3D box, you have to draw it in a 3D in a cubic box and try to separate it as a 1D box. So that will give you a better understanding because we understood 1D box well rather than a 2D box. So take a 1D box approach and try to understand it. Okay. Yeah. 35th question. The molar volume of an ideal gas 500 Kelvin and 100 bar is 0.416 decimeter cube per mole. Under the same condition, the molar volume of carbon dioxide is, okay. Based on this information, which of the following statement is correct? Okay. And so, what they are asking is, they are asking us to find the relation between the molar volume. So what they have given the molar volume of ideal and the molar volume of carbon dioxide, which is real. Okay. So you can say that molar volume of real is 0.366 decimeter cube and mole inverse. Okay. And then molar volume of ideal is 0.416 decimeter cube mole inverse. Okay. So here they are not asking us to find the percentage of difference, but even if you go and find the percentage of difference, the percentage of difference is going to be ideal. So V molar ideal by V molar real by V molar real. So this will give you an impact or correct definition, that when you actually substitute the values of molar volumes of real and ideal gas, you'll get the percentage around 12.02 percentage. Okay, the percentage is very less, and even without this, you can say that the molar volume of ideal gas is more than the molar volume of real gas, that the molar volume of carbon dioxide, which means that there is a attractive force dominating. Okay, so when there is a repulsive force, what happens? Your molar volume will be increasing. So the volume occupied by the carbon dioxide gas will increase the space if there is a repulsive force. But due to there is going to be an attractive force, what happens? The volume is going to shrink. They are going to occupy very less space. So option 2 is the correct answer. Okay. And this is a very simple ideology. Typically, question will be asked about the differences. Okay. Yeah. 36th question. The example of chain silicates and sheet silicates respectively are. So first we need to understand what is chain silicates and what is sheet silicates. So this is your example for your chain silicates. So where you can see all this orange dots are your silicons. Okay, your silicon will be typically surrounded by three oxygen atoms. It's going to be in the structure O minus O minus. Okay, so this is the actual structure for your chain silicates, and now they have given a different things. Okay, first let's focus on chain silicates. So first we have is deposite. Deposite is nothing but your magnesium and calcium. Okay, this is the example for your deposite. This is the example for your is diopside chain silicate. Okay, this is your diopside chain silicate. Okay, and then what is spodumene. Okay, so spodumene is nothing but this is also your chain silicate. So this is your chain silicate, and this is also your chain silicate, and the formula for this is going to be, this is called as lithium aluminum inosilicate. This is called your lithium aluminium inosilicate. Okay, so which means that this is also going to exist in the same manner only, but what will differ is, here we have magnesium ions, you can see, right? So here you have a calcium ion, here you have a calcium ion, here you have a magnesium ion. Likely there is going to be lithium and aluminum present in between your silicates. That's going to be your spodumene, and this is again going to be a chain silicate. Okay, then comes to kaolite. Kaolinite. Okay, kaolinite is nothing but this is your clay mineral. This is typically for your aluminium silicates only, but usually for the mineral of aluminium. Okay, and this is going to be this is also have a very similar formula, Al2O3. Okay, SiO2 and H2O. And this is the formula for your kaolinite. Okay. And if you see that this doesn't has a chain silicate formula. Okay, this doesn't has a chain silicate formula. The chain silicate formula is SiO3. The chain silicate formula is SiO3. Here we have only SiO2, so this is not a chain silicate. This is not a chain silicate. Then comes your deposit. Deposit, we know deposit is your chain silicate. Okay, and muscovite. So muscovite is nothing but your, this is going to be your sheet silicate. Okay, this is actually going to be your sheet silicate. So what is sheet silicate? Okay, let's try to understand. So sheet silicate is nothing but there is going to be an different arrangement, as you can see here, tetrahedral arrangement of silicates, and then there is going to be an octahedral layer of the metals. Okay, so here we have directly metals present as a ion in between the chain silicates. Okay, in between the chain silicates we have directly metals present in ionic forms, but rather here in your sheet silicates what typically happens is the compound, the whatever metal we have, that is going to have its own coordination spheres. Okay, coordination compounds in between the silicates. So that's why this is going to be called as sheet silicates. Again, there is a silicate layer of layers. Okay, so typically this will be in TOT structures with this tetrahedral, octahedral layer, and then tetrahedral layer. This is typically called as your sheet silicates. And here I have given the example for your biotite. Biotite is the example for your sheet silicate. So option D 3 is the correct answer. Okay, and you can see biotite actually has a silicon, aluminum, magnesium, and iron. Okay, then comes your pyrophyllate. Pyrophyllate is nothing but your feldspar. Maybe I think many actually know about this feldspar mineral. This is nothing but your aluminum mineral. Okay, so majority of the aluminum is actually extracted from this pyrolate. Okay, and this is also going to have a sheet silicate like structure, but this is typically for your aluminum, not for your silicates. Okay, so this is actually going to be your sheet silicate. So if you see, they are asking for the example of chain silicates and sheet silicates. So first one is chain silicates, and chain silicate cannot be the answer. Second one is again going to be, it's not a proper aluminum, but still this is again going to be your sheet silicates, and this is your sheet silicates. Deposit is your sheet silicate, chain silicate, and this is your sheet silicates. This is again going to be the structure. So that's why option 3 is the correct answer. Yeah, this is a kind of question, kind of tough questions. This is typically from your main group elements. Okay, 37th question. So if you don't even understand this one, don't think that you don't know anything. It's just that it is given in a very complex way, and you need to read the concepts in detail. Okay, so you don't have to worry more about this question. 37th question. Two liquid components of A and B are mixed together to form ideal binary solution. Okay, this is the catch. They are saying it's an ideal binary solution. Okay, so which means this is going to follow your Rowlett's law. This is going to follow your Rowlett's law. Okay, so what typically happens when you mix a two ideal solution together? Okay, so when you mix a two ideal solution, the enthalpy of heat is going to be zero. So del H of heat is going to be zero. Okay, so we can say that if there is a enthalpy of the enthalpy mixing of the pure component is, if the enthalpy of the pure component is going to be zero, then we can say that the volume mixing is also going to be zero. So why we say that uh, volume mixing is also zero when enthalpy is zero? So the enthalpy is nothing but the heat inside the, like, heat produced or decreased when we mix the two components, right? Enthalpy is the heat. If there is no change in heat or enthalpy, which means that we can say that there is no extra force acting on it. There is no attraction force, there is no repulsive force, so the volume is going to be remain same. The volume change is going to be zero. That's why we say dv mixing is going to be zero. Okay, and this will also follow your Gibbs-Duhem equation. But what we are looking for now, we are looking for your, they are asking about both the component follow Gibbs-Duhem Marcus equation. So Duhem Marcus equation is nothing but your modification of Gibbs-Duhem equation. So we know that Gibbs-Duhem equation is nothing but your potential compounds, right? So Na of d mu a is nothing but your chemical potential. This is your chemical potential plus Nb of d mu p equal to 0. So this is your chemical potential and this is your mole fraction. This is going to be your mole fraction. And this is your Gibbs-Duhem equation. The modification of Gibbs-Duhem equation is your Duhem-Marcus equation. Duhem-Marcus Marcus equation. So which is nothing but they are going to replace the chemical potential term with fugacity term. So if you replace your chemical potential term with fugacity term, then it's going to be your Duhem-Marcus equation. So for ideal binary solution, your Duhem-Marcus equation will be followed. So the formula is going to be Na do ln F by do Na pressure and temperature. So you can see that this Duhem-Marcus equation actually gives you a broader picture about what is happening. So you can see there is going to be the pressure and constant is same. Okay, at constant pressure and temperature. When I say there is no going change in pressure and temperature, again you can say that del V mixing is going to be, that is volume is going to be remain same. And you can also say that they have same vapor pressure because pressure we have kept as constant. So B, C, D is correct answer. And what about A? Okay. So what about A? Okay. I think I'm missing something. Let me see. Huh. No, no, no. Okay, we are going to keep the vapor pressure of A as constant and B as constant, which doesn't mean that these two are constant. Okay, so what about option A? So option A says that interactions are equal to AA interactions and BB interactions. So since it's an ideal binary solution, which means that the interaction between the component itself is going to be equal to the interaction between the solution. So when I say solutions, I say solutions of A and B. When I say the solution itself, which means a solution A and A itself. Okay. So this is going to be correct, and this is not correct just because we are taking two components. We are taking two different solutions. Okay. Each is going to be maintained at its own pressure. So it's maintained at its own pressure, at its own pressure. Okay, so that means the vapor pressure may or may not be same, but we cannot actually say. So option A, one is the correct answer. Okay, ratio of radius silicon and O2 minus is 0.029, suggesting the coordination number 4 for silicon and silicates. Okay, and the second statement is SiO4 4 minus ion is a tetrahedral ion, and in which silicon is sp3 hybridized. Okay, so we have seen the silicate structure in your previous questions. Your silicon belongs to your carbon family. So silicon typically belongs to your carbon family, where the coordination number is going to be 4. So the coordination number of silicon is also going to be 4. And what is the hybridization for your silicon? So we know that silicon is going to be again sp3 hybridized as like the carbon. Okay, so we can say that option statement 2 is correct. Likely the statement 1 is also correct because the coordination number for silicon is going to be 4. So the ratio in radius is also going to be 0.29. So both statement 1 and statement 2 is correct. So since it's an sp3 hybridized carbon, so it will have a tetrahedral structure. So this is going to be in a tetrahedral ion form. Okay, 39th question. in a nucleophile substitution reaction proceeding via SN2 mechanism, okay, which among the following will act as a good leaving group? Okay, so let's try to understand. So if you have a compound, so with a leaving group like this, and if you have a nucleophile, okay, so you need to have a good nucleophile. What happens in your SN2 mechanism? This nucleophile is going to attack from the other position, making the leaving group to leave. Okay, so your rate of the reaction. So your rate of the reaction typically below directly proportional to your leaving group ability and then your nucleophilicity. Okay, nucleophilicity of base. This is the equation for your SN2 mechanism. And now what they are asking? They are asking about the leaving group. So which will act as a very good leaving group. Let's try to end this step. Okay. So in cyanide, the cyanide can be actually represented as Cn. So you can shift the one double bond in either nitrogen or carbon. Okay, so it can be written as C double bond N minus, or it can also be written as carbanion with double bond N. So what this denotes? This denotes it's going to have a both pi acceptor and sigma donor ability. So this is not going to act as a very good leaving group. Okay, this can act as a leaving group, but comparatively this is not, because it has both characters. Likely your, and when it comes to your chlorine, so your chlorine is actually going to act as a pi acceptor. So it will take the electron completely and it will be readily moved. Okay. So your halogen compounds are always very good leaving group compared to other ones. So option 3 is the correct answer. So in option 4 we have a weak acid. Okay. This is a conjugate of your weak acid. Again, this is going to be not that much very good leaving group. So we can straight away say this is not at all a very good leaving group compared to your if you want to compare, your chlorine will be more than your cyanide, then comes your N3 group, then comes your acetate groups. Okay, next question, 40th question. In HCl molecule, the molecular orbitals will be formed by combining. So now we have to find the what are the molecular orbitals involved in form, formation of HCl molecule. So we know that hydrogen has only one electron, so which is going to be in 1s. This is going to be 1s prime. Comes here. Next comes here chlorine. What is the electronic configuration of chlorine? This is going to be 1s2, 2s2, 2p6, 3s2, and 3p5. This is going to be your chlorine structure. So in 3p5 it's going to be like this. So if you take the 3p, it's going to be like this: 1 2 3 4 5. So it can be in x, y, and z. Since they have given only one option with 3px, so option 4 is the correct answer. First question: for equimolar solution of acetic acid, dichloroacetic acid, and trichloroacetic acid, the depression in freezing point is maximum for. Okay, let's try to draw the structure. This is going to be your structure for acetic acid. COOH is going to be with three hydrogens. This is your acetic acid. Your dichloroacetic acid is going to be this. This is your dichloroacetic acid, and here comes your trichloroacetic acid. Okay, so if you see the alpha position, so wherever your carbonyl group is present, the next carbon is called your alpha carbon. In the alpha carbon, you can see here it has only hydrogens, but in case of your dichloroacetic acid and trichloroacetic acid, it has a electron withdrawing groups. Okay, so what that impacts, if you have a electron withdrawing group, strong electron withdrawing group, okay, if you have strong electron withdrawing group on alpha position, alpha carbon, your acid strength is going to increase, and which will also increase your degree of dissociation, which means it can be removed, the ability to remove the groups. Okay, degree of dissociation is going to be high, which eventually backed up with the factor, Van 't Hoff factor. Okay, so with Van 't Hoff factor you can say that your depression and freezing point is also going to be high. Okay, so let's try to compare. So we have dichloroacetic acid and trichloroacetic acid. So we have three chlorine atoms in your trichloroacetic acid, which means that your trichloroacetic acid is going to have high depression and freezing point. So option 3 is the correct answer. Okay. So in case of your chlorine, if they have given fluorine and chlorine, if they are asked a comparison between fluorine and chlorine, then your trifluoroacetic acid will have high depression and freezing point. 42nd question. Which of the following anions on reaction with alkyl halide favors elimination over substitution if effect of solvent is considered negligible? So what is alkyl halide? So let's say I'm considering a group like this. This is going to be your alkyl halide. We can say this is your alkyl group and we have a halide. This is your alkyl halide. Now we have to treat it with all the four anions given. Okay. So let's try to see. So first we have your bromine. Okay. So if you treat it with bromine, okay, if you are going to do the reaction, if you are going to eliminate this reaction, so if you attack this position, if you attack this carbon, your first carbon, okay, and making it to remove the bromine group, this is going to be your substitution reaction. So in order for an elimination reaction, you need a uh, good base. You don't need a nucleophile. So we know that bromine is going to act as a nucleophile, iodine is going to act as a nucleophile, okay, and your CH3 COH acetate is going to act as a base, a nucleophile only, because this is a weak base. This is actually a weak acid, so this is not actually a very good nucleophile, okay. And then comes your C2H5O minus, so which is actually your group like this. It's going to be like the CH2 CH3. Okay, this is going to be the structure of C2H5O minus. What this does is that this is going to abstract the hydrogen. Okay, so what it does is this is going to abstract the hydrogen, thereby it is going to form a carbanion, and this carbanion is going to kick the bromine out. Okay, this is your elimination reaction. So option 2 is the correct answer. Okay, so if you see in case of option 4, we have a carbonyl group, so which is actually your pi acceptor. So it cannot actually, it has very less basicity compared to your other group. Okay, compared to your ethoxy group. So this is your ethoxy group. Okay, yeah. Predict the major product in the following reaction. So they have given a 1, 2, 3, 4. Okay. So they have given a 2,4 dinitro chloro group. Okay. Dinitro chlorobenzene group. So this is your 2,4 dinitro chlorobenzene. Dinitro chlorobenzene, and we are treating with alkali. So the alkali can be potassium or it can be sodium or it can be anything. Let's say we have your sodium. So sodium will be exist as Na, right? So we'll take NaOH as an example. So what is going to do is like the NaO minus group, okay, which is your oxide group, is going to literally attack this position, thereby it's going to remove the chlorine group like this. So in place of sodium, you can also have potassium or any group. So what it does is that you are going to have your nitro in the same positions. Your nitrogen is not going to nitro group is not going to be changed, but rather in the place of sodium hydroxide, you are going to have a, sorry, in the place of chlorine, you are going to have sodium group. Okay, on further hydrolysis, this is going to be converted as alcohol. So this is the final structure. So this is going to be this. So you can see that the structure is 2,4 dinitrophenol. This is your famous reaction. So option 1 is the correct answer. Okay. 44th question. When two phases are in equilibrium, okay, so we know that we have actually seen many questions, like in the same question paper itself, we have seen many questions. When two phases are in equilibrium, when the two phases are in equilibrium, which means the two solutions or of the two phases are going to be ideal, okay. then the chemical potential of two phases is going to be same according to your Gibbs-Duhem equation, and there is no change in Gibbs free energy because they are same. And we know that according to Duhem-Marcus equation, the pressure and temperature of the compounds are going to be kept constant. Okay, so temperature and the pressure of the uh, compounds are going to be kept constant. So all of the above is the correct answer. Okay, 45th question. Okay, what they have asked: 25 percentage of first order reaction completes in 2.1 into 10 power 6 seconds. How much time is required to complete the reaction? Okay, so we know the first order formula. K is equal to 2.303 T. This is going to be 25 percentage, right? 25 percentage is nothing but T 1 by 4. Okay, into log 100. So see, initially there is going to be 100 percentage. Only 25 percentage is completed. Okay, so only 25 percentage is completed, which means there is only 75 will be left. There is only 75 is going to be left. Okay, so with this we can say, if you solve this one, if you try to substitute the values, 2.303 by 2.1 into 10 power 6 into log of 100 by 75. Like, there is another way to solve this question. If you could clearly know, for a first order reaction, in order to complete the full reaction, you need infinity times. Okay, the reaction cannot be completed within a short range. So the reaction of the first order is going to occur repeatedly. It's going to take infinity. It cannot be completed to 100 percentage. So option 4 is the correct answer if you know the concepts. If you don't know the concepts, you can simply solve this question. So you can also get the value of K around 0.136 into 10 power minus 6. Okay, now you can again substitute in the same formula. So we know that, so I'll just rewrite this question. So T 100 percentage is going to be equal to 2.303 by K log of A by A minus X, correct? So A is going to be 100. This is your A, and A minus X. So there is a 100% completion, right? So your A minus X is going to be 0. So this is going to be 100 by 0. So we know that 100 by 0 is nothing but your infinity. So log of this entire term is going to be infinite. Log infinity is again going to be infinity. Anything multiplied with infinity is going to be infinity. So the time taken for this reaction is going to be infinite. Okay, so option 4 is the correct answer. Next question: consider the electrode potential diagram for fluorine. Identify the species capable of disproportionating in aqueous solution. Okay, so first we need to understand the oxidation state of this groups. So, okay, they are talking about fluorine group, so we need to focus on the oxidation state of fluorine. So if you see, this is actually ClO4 minus. So the oxidation state of fluorine here is actually +7. Okay, in order for this species to disproportionate, it need to actually gain one more electron, but it's going to be not possible just because it's already in its high oxidation state. It's the ClO4 minus is actually in the high oxidation state, so it cannot gain electrons. So this will not undergo this proportionation reaction. So let's come to this group. Your ClO3 minus is going to have +5 oxidation state. So this will undergo your disproportionating reaction, and here the chlorine oxidation state is going to be +1. So it can occupy one more electron, like electrons. So this is also undergoes your disproportionation reaction. So option 2, your ClO3 minus and OCl minus is the correct answer. Benzene bond is formed by. So we know how benzene is formed. So if you have a group like this, if you have a benzene ring with some leaving groups, okay, if we are going to have a base, the base is going to abstract the hydrogen, thereby it's going to form a bond like this. This is going to be your benzene formation. So your benzene ring will be formed like this. So we know that in benzene, all carbons are sp2 hybridized. So there is going to be sp2 hybridization, sp2 sp2 overlap. So option 1 is the correct answer. 48th question. This is a straightforward question. The properties used for calculating Pauling's electronegativity and Millikan's electronegativity respectively are. So your Pauling electronegativity can be calculated using your bond energy, and your Millikan electronegativity can be calculated using your ionization energy plus electron affinity. So option 1 is the correct answer. So option 1 is the correct answer. Next question. 49th question. So they have given a reaction and therefore asking us to write the rate of the reaction. So they have given 2 moles of N2O5 reacts to give 4 moles of NO2 plus O2. Okay, so we can say that, so 1 mole of N2O5 is going to give 2 moles of NO2 plus half O2. Okay, so if you write the rate of the reaction, it's going to be minus d of N2O5 by dt. This is your rate of the change in concentration with time. Okay, is going to be equal to 1 by 2 of d NO2 by dt plus 1 by 2 d O2 by dt. Okay, so if you see the options, you can see this is going to be your correct answer. Only they are asking about the nitro groups, not the oxygen group. So if you compare, you can see option 2 is the correct answer, where they have given a negative charge, because this is in the reactant side. So you'll have a negative sign. Okay, this is important. 50th question. Again, a statement based question. To form interstitial alloys, okay, this is a straightforward question again. Okay, to form interstitial alloys, the radius ratio of smaller atom and larger atom should be in the range 0.414 and 0.732. So this is can be shortly remembered as root 3 minus root 2 minus root 3. This is a correct statement. Okay, two different metals having metallic radii differ only by 10 percentage, but similar crystal structures can form good alloys. Again, a correct statement. So you can say both statement 1 and statement 2 are correct. So we'll solve the rest of the questions in the next video. Thank you. Happy learning.